Hello everyone, welcome back to the class. In the last lecture, we talked about single slit diffraction. Okay? We will extend that knowledge, and now today we will discuss double slit diffraction. Now, this is the schematic of the double slit. The each slit is of length L, this length is L, and each slit is of width B. Okay? But slit to slit separation is A here. Okay. The slit to slit separation is being measured from the center of one slit to the center of the other slit. Okay. This is also shown here. This figure I took from the book Hecht, Optics by Hecht. Now, also pay your attention to the orientation of axes. The x axis is in this direction, and the z axis is along the in the plane of the this aperture, which is your double slit, and this is your z axis, and y is pointing upward, which is shown here. Okay. Therefore, I will just draw it for the clarity. Y is in this direction, x is here, and z is in this direction. Now, the origin is placed at the center of right slit. Okay. It can be placed at the center of any of the slit, but I chose to place it on the rightmost slit. Now, the angle in this case is being measured from y x plane, okay, which is shown here, and P is our point of observation. Now, this is how the fringe pattern of the slit look like, but we will discuss it in detail after the mathematical analysis is complete, and we will also discuss this figure 14C after the mathematical analysis is done. Now, here we consider two long slits, each of width B and center to center separation A. Now, once we were having single slit, then we divided this the width of each slit into finitesimally small width, which was of delta z length long, and then using the Farman analysis which we performed in the last class, we reduced the each line source with a point source, which was emitting circular wave. Okay. Now, we will do the same here too. Okay. Now, each slit will generate a single slit diffraction pattern on the screen, okay, and this is what is written here. Each aperture would generate a same single slit diffraction pattern on the viewing screen sigma. The flux density distribution is the resultant of rapidly varying double slit interference system modulated by single slit diffraction pattern. Okay. It says that since we have two slits, each slit will generate its own diffraction pattern, and these diffraction patterns are slowly varying. Okay. The maxima and minima, the separations are slow. Now, since we are having two slits, and the diffraction pattern between these two slits, the light which is coming out of these two slits, they will interfere among themselves, okay, and this will create a rapidly varying maxima minima, a rapidly varying fringe pattern. This rapid variation of fringes would be enveloped by a diffraction pattern. This rapid variation would be modulated by a slowly varying diffraction pattern. We will see in the forthcoming slide, we will see how does this happen. Now, we will follow the same analysis as we did for the single slit. Each of the two aperture or each of the two slit is divided into differential strips of width dz and length L, which in turn behave like an infinite number of point sources aligned along the z axis. What I mean to say is that, suppose this is our two slit arrangement, then this would be replaced by two horizontal line sources. Okay. This is exactly what we also did in case of single slit. Okay. This is the aperture, okay, and this is the modified line sources, okay, because we know that each vertical line source behave like a point source which emit a circular wave. Now, the total contribution to the electric field in the Fraunhofer approximation will be given by equation number 23, which we derived in the last lecture. And what is equation number 23? This is our equation number 23, and this is derived for a slit whose length is d, okay, and the origin is at the center of this line source. Now, since we are two line sources in two slit case, therefore, we will have two such integrals. Okay. One is extending from minus b by 2 to plus b by 2. Why? Because these are the two slits which we have right now, and origin is here, okay, and the slit width is b and the center to center separation is a. Therefore, for first slit wherein our origin is placed, the z, which is this axis, this varies from minus b by 2 to plus b by 2, okay, which is very much clear. The b is here, sorry, the z axis is in opposite direction, it is pointing in this direction. Therefore, it would be plus b by 2 here and minus b by 2 here, but if we move to this edge, this edge is a distance away from the origin, is the center of this, and then you will have to subtract minus b by 2, then a minus b by 2 is this edge, a plus b by 2 is this edge, okay, and this is how the limits are chosen in this particular case. Okay. And if you sum these two integrals up, this will give you the resultant field on the screen. Okay. Now, what is f? F is nothing but this integrand, okay, sin omega t minus k in bracket r minus z sin theta. We are having z here instead of y, because initially the line source were along y axis, but now the new line sources which we found by reducing the two slits, they are along z axis. Okay. Therefore, we replaced y with z here. Okay. There is a constant c is appearing here. This is this represents the source strength per unit length along z axis, and which is divided by r, of course. Okay. And this and what is r? R is measured from the origin to P, the point where the observation is being done. We will be concerned only with the relative flux density on sigma. We will not pay our attention on C. Why? Because the actual value of C is of little interest. Okay. Once the relative value is considered, then we will have C both in the numerator and denominator, and it will go away. Now, we will perform the integration, and integration yields two terms. This is the first term and this is the second term. First term is from first integral, second term is from the second integral. Okay. Herein you see there are two terms which are appearing, alpha and beta. Alpha is defined by Ka by 2 sin theta and beta is defined by Kb by 2 sin theta. Okay. Just remember, B is the width of the slit in double slit, width of the each slit, and center to center separation is small a. Now, the distance from one slit to P is r, giving a phase contribution of minus k r, which is appearing here in the first term. It is the first slit at which our origin is situated, and since we know that the slit is now reduced down to a line source which is now horizontally placed, and r is being measured from this horizontal line source to the point of observation P, and therefore, this phase part is coming due to the origin to the observation point distance. The distance from the second slit to the P is r minus a sin theta, okay, which is very much clear from this figure. This is the second slit and the point of observation P is here, okay, and this would be r minus a sin theta. A is this distance, center to center distance is a. Okay. Therefore, r minus a sin theta, where a is also appearing in alpha, we can write it as r minus 2a alpha by k. Okay. Now, if you see that this r minus 2 alpha by k is associated with the phase term which is appearing in the second term of equation number 37. Okay. Therefore, this term which is responsible for this phase, yeah, is again due to the distance from the center of the second slit to the point of observation P. Okay. Therefore, these expressions are very much clear. This is a time dependent phase, and the second term which is appearing in the phase part is due to the separation of the center of slit from the point of observation P. Now, we also have the quantity beta in the expression. The quantity 2 beta is the phase difference k into cap lambda between the two nearly parallel rays arriving at point P on screen from the edges of one of the slit. Okay, this point says that suppose this is one of the slit. Okay. Now, suppose let us pick different color. This is our point of observation P, then one ray is coming from this edge to the point P, other ray is coming from this edge to the point P. Okay. Now, there is a path difference between these two rays. Okay. Say this path difference is cap lambda, and now then you can calculate the phase difference between these two rays, and the phase difference would be k into cap lambda, and this is equal to twice of beta. Okay, and this is what is being said in this line. The quantity 2 beta is the phase difference between two nearly parallel rays arriving at point P on sigma from the edges of one of the slit. Okay, these 2 points are on the edges of the slit, and they are coming to the, and the rays originating from these edges are coming to point of observation P. Okay. But do remember, this slits has now reduced down to this horizontal line source, and these lines, this rays are coming from these edges. Okay. Now, the quantity 2 alpha, what is the 2 alpha here? Now, 2 alpha is the phase difference between two waves arriving at point P, one having originated at any point in first slit, other coming from the corresponding point in second slit. Now, suppose the line sources which we generated from the two slits are represented by these two horizontal lines. Then suppose the point of observation P is here, then if this is the ray which is coming from one of the slit, then the corresponding ray means this ray will also start from the left edge of the second slit. Okay. If we pick different point in the first slit, then if this is the ray which is coming to P, then the corresponding ray would be here at the center of the second slit. Okay. And the phase difference between these two or between these two now gives 2 alpha. Okay. Hope this is understood. Okay. And if it is unclear to you, then you can draw the whole slit like this. Okay. The same thing, same explanation is still valid here too. Okay. Now, from this expression 37, now we can write this expression. Okay. What is the difference? We just used sin C plus sin D formula, and then we have a bit simplified expression here. Once the field is known, we can calculate irradiance easily, which is given by equation number 39. Yeah. Now, here what we see is that we have a constant term which is 4 I naught, and then we have sinc function here, okay, which is contribution from the single slit. Okay. Each slit have their own diffraction pattern, and this resembles the single slit diffraction pattern, because in the single slit diffraction pattern too we saw this sin square beta upon beta square term. But this term is something new which is coming due to the presence of the other slit. Had there been only single slit, this term would have been there only, but cos square alpha term is appearing due to the presence of the other slit, the second slit. Okay. It means, had there been only single slit, we would have called it diffraction pattern, but now due to the presence of the other slit, the two slits, the beams coming from the two slits is now interfering somehow, and they are giving some interference along with the diffraction mix up. Okay. And this cos term is the interference, it represents the interference. Okay. But if you remember, in Young's double slit experiment also we were having this cos term. There we were having I is equal to 4 I naught cos square del by 2. Okay. The same term is appearing here. We will clarify it right now. Now, suppose in theta is equal to suppose theta is equal to 0, yeah, what would be the irradiance in theta is equal to 0 direction? In theta is equal to 0, I naught is the flux density contribution from either slit, and therefore, I theta 0 or I 0 would be equal to 4 I naught, and which is the total flux density in 0 direction, theta is equal to 0 direction. Okay. I repeat, when theta is equal to 0, I naught is the flux density contribution from either slit, and theta 0 is equal to 4 I naught is the total flux density. Okay. Total irradiance in theta is equal to 0 direction would be equal to 4 I naught, okay, which is also clear from equation number 39. Okay. The second point, if B becomes vanishingly small, and what is B? It is the width of the slit. Then Kb would be very small, and in this particular case sin beta by beta is equal to 1. If sin beta by beta is equal to 1, then we are only left with this term cos square alpha term, okay, and the equation reduces to the flux density expression for a long line source, that is Young's experiment, okay, because now we will have I theta is equal to 4 I naught cos square alpha, which is nothing but irradiance expression of Young's double slit. Okay. This expression we derived in Young's experiment. Okay, and this is very much obvious because we were having two slits and then we started reducing the width of the slit, then this will reduce to two line sources, okay, and therefore, we will get Young's type fringes, okay, which is also obvious with this expression. If alpha A is equal to 0, what is A? It is center to center separation, it is separation between the two slits. If A is equal to 0, then two slits will merge, okay, and if two slits will merge, then we will have single slit diffraction pattern, and if you substitute A is equal to 0, then alpha would be equal to 0, and therefore, cos square alpha term will give you 1, and what we are left with is this, okay, I theta is equal to 4 I naught sin square beta by beta square, and this is equivalent for single slit diffraction with source strength doubled. Okay. The source strength here is now doubled because two slits are being merged. Okay. Now, the last point here is that we might envision the total expression as being generated by cos square alpha interference term modulated by sin square beta by beta square diffraction term, which is what I said earlier. This is your interference contribution, and this is very obvious diffraction, single slit diffraction. Okay. This is the interference term, cos square alpha term is rapidly varying function. Okay. Alpha is here, K A by 2 sin theta. Okay. A is large as compared to B, therefore, cos square alpha will vary rapidly. Beta is smaller, K B by 2 sin theta. Therefore, here diffraction is a slowly varying function and interference is rapidly varying function. Therefore, diffraction will modulate the interference term. Now, let us talk about maxima minima at angular positions where beta is equal to plus minus pi, plus minus 2 pi, plus minus 3 pi, that is integral multiple of pi. Then what will happen? Diffraction effects are such that no light reaches to the screen, and clearly none is available for interference. Okay, at these values of beta, the diffraction minima appear. Okay, this is the condition for diffraction minima. Now, at these values of alpha, the interference minima appear, okay, and the various contribution to the electric field will be completely out of phase and will cancel regardless of the actual amount of the light made available for diffraction process. Okay. It means at few certain angles diffraction minima will appear, while at certain angle interference minima will appear. Okay. Similarly, at center certain angles interference maxima will appear, at certain angle diffraction maxima will appear. Now, if A is equal to MB, then you can see that here m is a number integer, then there will be around 2 m fringes within the central diffraction peak. Okay. suppose this is our diffraction peak, then in this diffraction peak we have multiple number of interference peaks, okay, as shown here in the first slide. Okay. You can easily calculate the maxima and minima of diffraction and interference from the conditions, and you see that this envelope is diffraction envelope, while these the shaded peaks are interference fringes. Okay. Due to diffraction, these interference fringes gets modulated. Okay. You see that you get several interference maxima, okay, but only one diffraction maxima within certain angle range. Okay. Diffraction interference fringes are sharper, they are thinner, while diffraction fringes are broader. Therefore, diffraction very slowly, while interference very fast, rapidly in terms of theta, of course. Yeah. Now, you see that it may so happen that interference is having its maxima here coincide with the diffraction minima, then what will happen? Okay. This is entertained here in this point. At an interference maximum and diffraction minimum may correspond to same theta value, then what will happen? Interference says that there should be irradiance maxima, while diffraction says that there should be irradiance minima, then what will happen? In that case, no light is available at that precise position to partake in the interference process. Okay. Since there is a diffraction minima, there will not be any light to interfere, and the interference peak would be suppressed, it would be absent from there, and the suppressed peak is said to be missing order. The interference order would be missing, this suppressed peak. Now, you see here the same thing in the first slide. In this slide, this is the zoomed in figure. Okay. This area is zoomed in here. You see that these are the interference fringes. Now, interference says that there should be a maxima here. Okay. This is how it should go, but what happens exactly is that the diffraction minima falls on the interference maxima. Therefore, there is no light to partake in the interference process. Therefore, we get a missed interference order, and therefore, this is called missing order. Okay. And this figure is also shown here in this slide. Okay. Sin theta value of lambda by V, we see a missing order when A is equal to 3B, or when fringe to fringe separation is 3 times the fringe width. In this particular case, at sin theta value of lambda by V, we see a missing order. Okay. Had there not been a diffraction minima, we would have seen some peak, interference peak here, but it is not there. Due to this phenomena, we see only a partial peak here, partial interference peak here, and a partial interference peak here. These are called half fringes. Okay. And also make it a point. Now, you see that the fringes are it is a complete fringe here, this is a complete fringe, this is a complete fringe, but this is a half fringe here. Therefore, while counting the number of fringes within central diffraction maxima using this condition, if A is equal to MB, where M is any number, it says that there would be around 2m fringes within the central diffraction peak. This 2m number includes these half fringe or fractional fringes. Okay. They treat the fractional fringes as one. Okay. Now, this is all for today, and this completes double slit diffraction pattern or two slit diffraction pattern. Thank you for listening me.